We are going to start talking about functions today. Functions. Functions. Functions from one topological space to another. This is principally, functions are interesting on their own, but one big kind of, benefit or reason to talk about functions is we will finally be able to actually say what it means for two topological spaces to be equivalent, like the same as each other. For two topological spaces to be, I will say in quotes, the same. In order to make sense of this sameness notion, in most mathematical areas, that notion of sameness is expressed using functions. You've seen this if you've taken the abstract algebra class. Two groups are the same. What that means is that they are isomorphic, and in order to talk about what that means, you have to talk about a function from one to the other, which has certain properties. It's a bijection and some stuff about the operations, right? The same is true for topological spaces. So there is a notion about one topological space is the same as the other, and the way that the definition of that works is it's about functions. There's a function from one to the other, which is a bijection, and it also has some properties about something or other. That's where we're going with this. At least that's one of the places we're going with this. But there are other things to talk about with functions just on their own. But anyway, the basic kind of function that we're going to talk about in topology is a continuous function. The idea of a continuous function is like nearby points in the domain, they end up at nearby points in the codomain. And the important thing about a topological space is sort of like what's nearby each other, or really more technically, what are the open sets. So that's the proper idea of a function. So topological spaces have continuous functions, and those are the important kinds of functions to talk about in topology, right? In group theory, the important functions are group homomorphisms, some of which are isomorphisms. In linear algebra, the important ones are linear transformations. And in topology, the important functions to talk about are continuous functions. So we have to discuss the definition of a continuous function. What makes a function continuous? In the real numbers, the definition of continuous function is the epsilon delta definition. So I will remind ourselves of that. In the real numbers, continuous, I'll say f is continuous, means for all a in the real numbers, this I'm saying continuous at every point of the real numbers. It means for every point in the real numbers, it's this epsilon and delta thing. For all epsilon greater than 0, there exists delta greater than 0 such that. I hope you remember this, although we're not going to be using this definition. This is the epsilon and delta definition of continuity. All right. This looks like a bunch of nonsense if you don't already know what I'm talking about, but I think you do already know what I'm talking about. This is the epsilon and delta definition of continuity. Now, we are not usually going to use this definition, or maybe I will say we are not ever going to use this definition. It works fine in R, and it looks very confusing, but actually in specific examples, it's not so hard to work with in R to write proofs using the epsilons and the deltas. Once you know how to do it, it's not so hard to do. What was I going to say? Oh yeah, it's just that this definition doesn't really apply to most of our topological spaces that we're going to talk about, because it involves like subtracting the two things as if they were numbers and subtracting these 2 points here. In a general topological space, if I have two different points x and a, you can't just subtract them and you can't take the absolute value unless they happen to be real numbers. But we want to consider any kind of topological space. So we need to rephrase this rephrase without using something like absolute value of something minus something. That's really the problem with this definition from our point of view. In general topology, you can't do that part of it. That only works when you're dealing with numbers. So we have to rephrase this without using that. And I would like to draw your attention, cast your memory back in your real analysis class. I am sure that you saw this, you did at some point a proof of this, what at the time you probably thought of as an obscure fact, but this is a theorem from real analysis, is that f is continuous if and only if. So in an analysis class, this is written as a theorem, although we're going to use this as a definition. F is continuous if and only if whenever U, a subset of R, is open, then F inverse of U, which is also a subset of R, is open. This is a theorem that you proved in your real analysis class, and you probably don't remember it because it's not, I mean, by itself, this is not a terribly useful theorem in real analysis. If you want to show something is continuous, if you want to talk about continuity in real analysis, you're much better off using the epsilons and the deltas. This, though, is, I mean, I said we want to rephrase this without using this business. This is the appropriate way to rephrase this without using absolute values and subtractions, only using open sets, which is perfect for what we want to talk about in topology. All right. So actually, this is what we use as the definition of what it means to be continuous in any topological space. So this, we use this as our definition. All right. This right here is a if and only if, meaning this thing about the open sets is actually equivalent to the epsilons and the deltas. Only in a general topological space, we can't talk about the epsilons and the deltas. So we do it in this way instead. I will just write this as our definition. So F, well, I'll say it. Let's write it all the way out. So I'm going to say let X and Y be topological spaces. And a function F going X to Y. All right? So they don't have, neither one of them has to be R. They can be two different topological spaces, and you have a function like this. Then F is continuous. If and only if U in Y is open, then F inverse U in X is open. I don't know why I wrote the word in. This should be a subset. All right. It's a little weird that we use the inverse rather than just F itself, but I'm going to talk about why, in fact, that is necessary. I'm not just sort of doing it backwards for fun. You actually need to use the inverse there for somewhat strange reasons. But this is the definition of continuous. If you start with an open set in the codomain Y, you pull it back, the inverse image using F, then that has to be open. All right. So a shorter way of writing this is just U open implies F inverse of U is open. Right. That's what continuous means. This bears no resemblance really to you know, drawing the graph without lifting your pencil off the paper or something. But this is, if you're talking about real numbers for X and Y, it is equivalent to the epsilon delta definition. All right. U is open implies F inverse of U is open. So what this looks like in a in a standard picture, if I'm drawing this like functions of real numbers, say this, I'll make it a little curvier than that. Let's say this is my function, the graph of f of x. This is continuous the way that I drew it. I just want to sort of show what does it look like? What do I mean when we talk about this? If U is open in the codomain and you pull it back, you get an open set. So what that would look like in a picture like this is I can choose some set U in the codomain. So maybe U looks like a little open interval here, right, along the y-axis. I didn't really want it to go up to the top of that hump. It's a little ambiguous. Let's actually make it go. I'll make it go past the top, just so that it's clear. I mean, it could go either way, but it doesn't matter. All right, this is my U. What is F inverse of U? Actually, F inverse of U will be some set down here, right? It is all the points down here, so that when you plug them into the function values end up in U. I think the way that you can consider that is sort of if you look at kind of this horizontal band here. Wherever you see y values in that range, those points will get pulled back into U. So F inverse of U includes points here, because any point in here, when its y values are inside this band, so they end up inside of U. So these points here are part of F inverse of U. They should omit their endpoints, right? Because since the original set U omits its endpoints, in order to go into here, you should also omit these two endpoints. That's not the entirety of F inverse of U. It also includes all of these points here in the x-axis. Those also map inside of this band. And so you also get, and again, this must exclude the endpoints, you also get this part. So those two sets together is F inverse of U. Remember, F inverse of U, the pre-image of U is a set. And in this case, it's actually a disconnected set. It has two parts to it. That's the pre-image of U. All right? And do you agree that because U is open, that is why F inverse of U is open in this case? The reason why these endpoints have to be excluded here is really because these lines here are boundary values which are excluded. And so when you pull this back, this is open. So this is open, and this also ends up being open. All right? This is the picture of what it looks like when the function is continuous. Maybe we should look at a picture where it's discontinuous and see how the openness gets messed up. So here, that's a picture where it is continuous. And it's because any open set over here will pull back in the domain into an open set of the domain. But if it's not continuous, here's an example of a discontinuous function where you can see the openness gets messed up. So discontinuous would look like, one of those, something like that. So this one, not continuous, of course. And it will not surprise you that the way that I'm going to choose the U somehow involves like this point and this gap here. In this example, if I choose the U to be something like this, I'm choosing an open set over here, which sort of goes across part of the gap, but not all the way up to the top of the gap. Then what is the inverse image of that? Well, again, we would sort of think about the band of y values which end up in this open set. In this case, there's actually some to the left of the y-axis, but it doesn't really matter. All right. So I'm looking for all of the x values which end up inside of that, that horizontal strip. And there is a little bit over here, right? Not including that endpoint, going all the way up to here, specifically including that last point. And this is what makes it not open, is the fact that we have a solid point right there where the function just ends, but it includes that point. And so when I look for all the x values which end up in this band here, it goes up and includes this point, but doesn't have any more nearby. All right. So in this case, I have U is an open set, but here F inverse of U is not open. And that's because it's not continuous. All right. Let's So this is the what the picture looks like when it's not continuous. All right. One more simple drawing to show that this is a question that I raised, so I will remind you. Continuous means U is open implies F inverse of U is open. The pre-image of U is open, right? This you should definitely memorize, I guess. I mean, it's a fundamental fact that hopefully you will remember. I think a natural question to ask is, why you got to use the inverse? Because I don't like the inverse. I would prefer if it was just F. Actually, my first response would be, you kind of should like the inverse. It's a little weird, but it turns out for most of the things, actually for everything that we're going to use it for, the inverse is better than the ordinary function. So I would suggest that you truly do like the inverse, even if you think you don't. Actually, the reason you can't use just the F is that's not even true if you just used the F. So I will say, don't say U open implies F of U is open, because this isn't even true for continuous functions. I don't know if you ever thought about this, but it's just not true. And for example, it's not so hard to come up with, how about f of x equal x squared? I can find a u in the domain which is open, but f of u is not open. And it's not even all that weird. If I take, say, an open interval down here, you know, -1 to 1. What is f of u then? You can actually write it also as an interval. I want to know what are all the y values you can get by doing x squared here. Any ideas? This is not a trick question. Only half of us are here. Only half of the Julias. You don't have the other 2 Julias to save you. What do you think? Yeah?
0 to 1.
Yeah, it's 0 to 1. Is it the open interval from 0 to 1? You have to think, does it include 1 and does it include 0? Like, can you actually get the number 0 by squaring some number in here? I think you actually can, right? It's not like it approaches 0. Can you actually get the number 1 by squaring something in here? No, because this interval does not include the 1s. So the answer is that, all right? And that's not open, okay? So the moral of the story is, U being an open set does not mean that f of u is going to be an open set, even for a simple continuous function like this, all right? So here we have open, here we have not open, all right? So U being open implies f of u is open. That doesn't really mean anything. Actually, there's a name for that, but it's not a continuous function. A function which satisfies this property is called an open map. It means if you start with any open set, the image is also an open set. But that doesn't mean it's continuous. And in fact, you can have a discontinuous function, which is an open map, and you can have a continuous function, which is not an open map. They're just 2 completely different things. And actually, these kinds of functions, you can say a lot about what properties of open maps, but they're kind of weird. We are essentially never going to talk about functions which have this property. There are functions like that, but we don't care about them so much. All right. I thought we should talk about one example that's not just R to R, because everybody, I hope you all have good intuition by now about continuous functions R to R, but really we are trying to talk about continuous functions from a different, different kinds of topological spaces, not R to R. So remember, continuous, I'm going to write it again. Continuous, I will often just write CTS instead of writing out the whole word, means U is open implies F inverse U is open. If I write this down enough times, you will memorize it naturally. I would like to point out, actually, like when it comes to actually proving that a function is continuous, actually it's good enough, and this is a useful fact very often, it's good enough to assume that U is a basis open set. I've kind of already been doing that, but when I was drawing these pictures up here, I was always using actually one single open interval, although that's not what any open set looks like. Any open set could be a union of different open intervals in R. And but what I'm saying here is actually, if you want to show something is continuous, it's okay to just assume that U is a basis open set. It turns out if this property holds for the basis sets, it automatically holds for any open set. That's because an open set is a union of basis open sets, and then when you do the pre-image, it works nicely using unions. So it's good enough to only consider when U is a basis set. This will make proving something continuous a lot easier. You don't have to consider any open set at all, just a basis open set. Let's look at, so another example, not R to R, because those are fairly straightforward to deal with. Here is a fancier example. How about x equals the interval 0 to 1 with the subspace topology from R. And y is S1, the circle. All right. And the function is, I'm often going to draw sort of a diagram like this. F goes from x to y. So this is x over here. This is y. And what is the function? I mean, I'm using basically the quotient function that we talked about in the past, but it is the function which wraps those points around the circle and joins the two endpoints together. So this is the function which wraps the interval around so that f of 0 equals f of 1. All right? This is a function, and y, the topology on y, I guess I should say, is subspace from R2. Right? So the open sets in y look like little intervals along the circle, because that's what you get. Remember, the subspace topology means you intersect a ball from R2 with y, and it looks like a little interval inside of y. Okay, I would like to demonstrate that this is continuous, all right? I didn't really tell you a formula for f, so to show it's continuous does not involve actually computing the inverse image or anything like that. We're going to do this, try to do this in a more schematic kind of way. So let's show that f is continuous. All right? Of course, remember what this means is U is open in y implies f inverse of U is open in x. So I need to consider any open set in y. And like I said before, it's actually good enough if we consider it to be a basis open set. So I'm going to begin by saying let U subset of y be a basis open set. All right. And then I want to show the pre-image of U is open in X. All right. And what does a basis open set in Y look like? Well, I said before, U looks like, you know, Y is the circle, and then U looks like an intersection of a ball from R2. Look at my nicely drawn picture. Can you see that? I hope you can see that little dotted line there. That's a ball from R2, and when you intersect it with the circle, what you get is a little interval inside Y like that. All right? So this is what the set U looks like. That's what an open set in the circle looks like. And the question is, where are all the points that end up in there? Now, actually, you have to consider two different cases because the definition of F involves wrapping these points around the circle and joining those 2 points up. When you undo F, actually it matters if your set U includes that point where they got glued together, then undoing it will do something a little weird. But if the set does not include that point, then undoing it is very simple. So let's consider, actually, I want to consider 2 cases. One is like this, where the gluing point is outside of U. There's really going to be 2 cases. It's like that, or another situation where the point where I glue them together is actually inside of U, like so. And the open set this time looks like that, where it bridges across that point, all right? The pre-image will look slightly differently, so we need to consider these both cases. So here, this is U. Anyway, can we say what the what it looks like? So here, U looks like that. Then F inverse of U looks like, remember, this is what X looks like. And the idea here is if I take this circle and unwrap it, because that's what the ordinary F wraps it around and joins the ends together. If I take this circle and unwrap it, what does this U end up looking like over here? Can anybody describe in words what where that set ends up when you unwrap it over here? What do you want to say? What do you think?
It's just like an open set. It's closer to the left end.
Yeah, she says it's an open interval over here that's kind of close to the left. Yeah, if you imagine taking this circle and unwrapping it like so that the top half kind of goes over to the left, the bottom half stays over to the right. Yeah, then this U will unwrap into a set like this. This is F inverse of U. And is that an open set? Yes, it is. This is an open set using the subspace topology from R because it's just a normal open interval in R. So here I will say F inverse of U is open in 0, 1. Actually, it's an open set from R, but in particular, it is open in 0, 1 with the subspace topology from R as desired. That's the first case. All right? And then we also just have to demonstrate also in the second case what you get. In this case, then F inverse of U looks like, can anyone say this time? Someone else maybe? What does it look like when you unwrap that set onto the interval this time? Anyone else want to say? Is this hard, or just nobody wants to say anything? What do you think?
Like you have like the 2 ends, so you have.
Yes. Yeah, you get sort of this bit here. If you unwrap that, it gives you like a little bit on the left end, and then you also, from the other side, you get a little bit on the right end. That's what it looks like. And I believe they're sort of open circles either way, right? Like this, and then also like this. That's what F inverse of U looks like this time. It's a disconnected thing in 2 pieces. And is that an open set in 0, 1 with the subspace topology? It is. It looks a little weird because of the filled in, endpoints here. These are not traditional open sets in R, but using the subspace topology, this is an open set because you can make it from 2 real open intervals like this that just overshoot the ends. And when you intersect that with the interval, you get this thing. So I will just write the same thing again. Here, f inverse of u is open in 0, 1. Since we're using the subspace topology, it's a little weird looking, but it is an open set as desired. All right, so this is a continuous function. As it should be, right? When I think about what a continuous function is, sort of on an intuitive level, on a spiritual level, it is some kind of function which takes the first space, like in this example. You start with this line and you wrap it around into this thing. To me, continuous in topology means something like you stretch the thing around maybe, and perhaps you glue some points together, but you never rip it apart or cut a tear in it or something like that. This is on a vague level how you should feel about continuity. So when I describe this function, this one definitely seems continuous to me because it involves some gluing but no ripping. Although a function going back the other way cannot be continuous unless it's a stupid function like a constant function. Just make all these points go to the left endpoint. That's continuous, but it's not very interesting. Did I say cannot be continuous? I shouldn't have said cannot be continuous, but there is no such thing as like unwrap the circle in a continuous way because that involves cutting it off. All right, excellent. All right, we got 15 minutes. I think this is enough time to talk about, really I have two theorems about continuous functions to discuss in this section. We'll get to one of them. We'll do one today, and then we'll do one next time. Two theorems about continuous functions. And I have kind of a theorem number 0, which is going to be on the homework. Then I don't want to really spend time on it, but we're going to, it is occasionally useful. So theorem number 0, which you're going to do on the homework. It says f is continuous if and only if u closed implies f inverse of u is closed. It turns out in some cases it is more convenient to work with closed sets rather than open sets. And it turns out the definition of continuity, which usually we write in terms of open sets, is actually the same if you consider closed sets. A closed set in the codomain pulls back to a closed set in the domain. Why does this work? It's because closed means the complement is open, and so if you have a continuous function, you can use the ordinary open definition, but just like take the complement of everything, and it gives you this version of it. You'll work this out on the homework, but that's sort of theorem number 0, which I don't really want to talk about. We are going to use it every so often though, so I wanted to mention it at least once in class. Let's talk about theorem number 1, which is about actually both of the real ones that I want to talk about are about combining continuous functions together. Combining continuous functions. There are two ways that we're going to talk about combining continuous functions together. The first one, which we'll do today, is the simple one. The standard way to combine functions together, I mean, in calculus or something, you might add or multiply them together, but we're not going to do any of that because topological spaces don't have operations on them. But the standard way to combine two functions together is the composition. You do one, and then you plug it inside of the other one. So combining continuous functions together. The setting of this one is if I have sort of some space x and a y, and I have a function that goes like this, and then I have another function which goes like this, y to z, say. This is the setting in which you can make the composition. You do f and then g, right? F followed by g, or f first and then g. And if these functions are all continuous, the theorem says if f and g are both continuous, then the composition is also continuous. That's what the theorem is about. And this should seem sort of intuitively clear. If I do F, if F involves no ripping or tearing, and also G involves no ripping, then if I do F followed by G, that should also involve no cutting or ripping. So that's the intuitive notion, but of course that's not a real proof of this. So I'm going to write this. The theorem says, let X, Y, Z be topological spaces, and let F be some function X to Y, be continuous, and G is some function Y to Z, be continuous. And then the conclusion is then F, actually it has, just because of the way I set this up, it has to be G composed with F, right? You do F first and then G. As you all know, writing a composition is a little confusing. You sort of have to write them backwards. What are the domain and the codomain for this? The domain is X because I'm doing F first. So the thing you plug in first has to be X. And the thing that comes out of the result is a Z. So this is like that. Is continuous. That's what the theorem says. If I have two continuous functions, compose them like that, the result is continuous. All right. This is a basic kind of thing that you do in pretty much all areas of mathematics. If you have a certain type of function that you like to talk about, this is one of the first theorems that you ever prove about it. I'm sure in your group theory class, one of the first things you said about homomorphisms of groups is that the composition of two group homomorphisms is also a group homomorphism. Or we talked in linear algebra, you showed that the composition of two linear transformations is also a linear transformation. This is like a classic kind of theorem that you always prove about your favorite kinds of functions in whatever setting. And usually this proof that you do is not very difficult. And it's not really very difficult in this case. We have to show, so let's write down what we want to show. We want to show this is continuous, which means, of course, U being an open set implies, usually I say F inverse of U is open, although it's not F, it's this. All right, so the way we structure this proof is I say let U, a subset of Z, be open, and then we'll show that G compose F inverse of U is open, right? G compose F, the preimage. And the idea of the proof is this G composed with F is doing both functions at once, but you want to think of it as doing one at a time. First you do F and then you do G. So this is not so difficult to think through. G composed with F inverse of U. I want to rewrite that as like something first and then something else. Something like, is this G inverse of F inverse of U? Like, I want to somehow deal with this as two inverses, right? What if I say, you should ask yourself, is this really true? Can you do that with a function inverse image? This would mean pulling the U, remember the picture is kind of like X is here, then Y, then Z, and U is over there. You pull it all the way back. This is the same as pulling it back through F first and then pull it back through G. Is that true? There's something not quite right about that. Yeah, what?
It's the opposite, so it's G inverse of F. Like, just switch the F.
Yes, you do it the other way around. This is a basic fact about inverses, which I'm sure now that she says it, probably you remember. If you want to invert, this one over here says you do F first and then G. The opposite of that would be undo the G first and then undo the F. This is the old, every morning I put on my socks and then I put on my shoes. And how do you reverse the process? You take off the shoes first and then the socks. When you do it backwards, you got to do it in the other order. Anyway, this is a true fact about inverse images. All right. Okay. Anyway, does this help anything? Well, we assume that U is open here. So I think that means something about this. Can anybody say, what does that mean using the fact that since I'm going to say G is continuous. Anybody see where I'm going with this? What can you say about that? U is an open set and G is continuous. What does that mean?
G inverse U is open.
Yeah, it means G inverse of U is open, right? Because U is open and G is a continuous function. So that means G inverse of U, which is what you see right here, right? That is open. Right? In Y, I guess, right? We pulled it back one step. But now I'm going to say since F is continuous, can anyone say what can you conclude from that? Maybe somebody else who is not a Julia. I welcome non-Julias also to participate. I know there's not a lot of you. Yeah.
Can't you say F inverse is open? G inverse.
Yeah, F inverse of this red thing, right? We just said the red thing is open, and since F is continuous, it means you pull back a open, you get a open. So since F is continuous, this means F inverse of G inverse of U is open. But actually that's what we wanted to show, right? Because that, what it says at the top there, that is equal to G compose F inverse. So that is open, which is what I said we were going to show from the beginning. All right. The very short version is, you start with a set in Z and you want to pull it all the way back and make sure it's still open. Well, you pull it back one at a time and it stays open each time because the F and the G are both open. So that's why it's open in the end. All right. So the composition of two continuous functions is a continuous function. Great. And I got one more. So the next theorem is a little more complicated, and maybe we can take the next 5 minutes just to think about what it means, and then we'll do the actual proof next time, which the proof, again, is not all that difficult. But our next one is, so this is like theorem number 2. It's a little strange, and by itself is kind of interesting, but actually the book calls this a lemma. You usually use this to prove other things. That's what a lemma is. It's like a theorem, but principally used in order to prove other theorems. It's called the pasting lemma. And this is another way of combining continuous functions. And this is this is about sort of the situation when two continuous functions have overlapping domains. All right, so if you're thinking about a real valued functions, you might have, say, F looks like this, maybe only defined on an open set is fine, and then G looks like this maybe. So here's two functions with overlapping domains. They don't have the same domain, but their domains have some points in common. In this case, the overlapping domain is right here. All right, those are the places where the two domains overlap. But anyway, this is the pasting lemma. It's about, can you glue together two functions like this to make a continuous function out of it? Now, these two functions cannot be glued together to make a function, a single function, because F and G, where the domain overlaps, they have different function values here, and there's no There's no standard way to rectify the difference. But the theorem says if f and g have the same values on the overlap, then you can stick them together and create one sort of big function. So the picture, these, I will say these can't be pasted because they're different along the points where they overlap. They don't give the same answers. But you could have, you could imagine a scenario like, say, f goes that far and g goes like this, where they actually agree on the overlapping part. Then you can imagine sort of combining them together into one big function. And that one big function will still be continuous. All right? So here, they can be pasted into a big function. And that big function would be, you know, well, just be like that, right? All those values taken together into one big function. This is the pasting lemma. All right. So our topological version of this would look. The pictures aren't going to look like this. These are pictures in R. But topologically speaking, the topological space version is something like you have your domain X, which consists of sort of two pieces, A and B. And A and B are the domains of F and G. And so F carries A somewhere. This is F of A. And then G carries B somewhere else into some other set. This is G of B. And the theorem will say if F and G actually agree in the overlapping part, if the values are all matching in the overlapping part, then you can create one big function over here, and it will still be continuous. That's the idea. So if F and G are continuous and they agree on A intersect B, then they can be, maybe I'll just say they can build a function on A union B, which is continuous. All right. If the two functions' values are the same where it overlaps, then actually you can create a big function whose domain is everything, all of A and B together. That's why this is A union B. And that function will still be continuous. All right. That's the idea. This is just a schematic kind of picture, but we'll write some more details of this next time. All right. I think that'll do it. You should expect some homework, probably shorter than usual because we haven't done all that much, but maybe some basic stuff about continuous functions.